welcome to Lab 3. And this week we'll go through D-type flip-flops, how these flip-flops will form counters, and then we'll give you two types of counters. So you have your sequencer, which is an asynchronous counter, and a synchronous counter, which is your binary coded decimal counter or BCD counter. And then we'll finalize the video with the tasks expected from you for Lab 3. D-type flip-flops are positive edge triggered flip-flops, so the data stored in the flip-flop will only change when a positive edge is sent to the clock input. So as you can see from the image on the left, you have your SR latch over here with another flip-flop in there, and your D-type flip-flop is formed out here. To make it a positive edge triggered flip-flop, the inverter is added into the clock input. So these should be explained in your lectures, so refer to the lecture videos if you're still unsure about that. And to the right here is a brief logic diagram of a flip-flop. So you have a storage element, and your next state will be based on your current state as well as your inputs. And then when the positive edge triggers this flip-flop, your output will become the next state. Now, in Xilinx, the D-type flip-flop is seen on this picture on the left. It is FDC, and if you type it in the symbols tab, you should be able to find FDC. Now, do note that in Xilinx, there are two types of D-type flip-flops, FDC and FDR. The difference between them is the way they clear or reset their storage element. So FDC is flip-flop D-type asynchronous clear, and FDR is flip-flop D-type synchronous reset. So in FDC, whenever a clear signal is sent in, the storage element resets without any regard to whether or not the clock has been triggered. However, with an FDR, with a synchronous reset, when a positive edge is inputted into the clock input, your reset line will be checked, and if that is a high, then the storage element resets. Now to the operation of D-type flip-flops, so you can see the output Q is the input data, D when a positive edge is triggered. So if you look on the image to your right in this state sequence, you can see your clock input over here. So the clock just goes high, low, high, low, high, low at a predetermined speed. Obviously, this clock input that you feed into this clock does not need to be a clock from your hardware itself. It could be a signal you send from another part of your combinational or sequential circuits. So as your clock goes positive edged, your data storage element changes. So do note that even though your input's changing over time, the output Q is only changed when a positive edge is triggered. So in this case, you can see that there are only 3 sets of positive edge triggers, even though your input has 2. Now let's consider this configuration of a D-type flip-flop. So what would be the output? So as you can see over here, you have your clock in, and on your output, the output is inverted and fed back into your input. Now the output over here is still inverted because it is to the right of the inverter. However, if this inverter was in this feedback loop, your output would then be the true output of your D-type flip-flops. But in this case, when there is a positive edge on the clock input, the output complements. Counters are sequential circuits which count through a sequence. These sequence can either be mathematical based or binary based, or it could be based on a user-defined constraint. This sequence is designed and drawn by the author. However, with counters, there are 2 distinct types of counters. You have asynchronous counters and synchronous counters. Asynchronous counters means that part of your circuit will not be dependent on the clock input. So an example of that are ripple counters or sequences, which we'll go through in a short moment. And then on the other hand, we have synchronous counters, which are counters which count or sequence through a set sequence as determined by the clock input. And in our case, the BCD counter is an example of that. The outputs of the D-type flip-flops in ripple counters are then connected to the clock input of the next flip-flop in series, and then the input for each of the flip-flop is the complement of the output. We will look at this schematic in a short moment, but as you can see that the output of one flip-flop is connected to the clock input of the next flip-flop. Now, between the output and the input, there is an inherent mechanical delay between the signal being outputted from the flip-flop to the input of the next flip-flop. Thus, the name of these type of counters are called asynchronous counters, because even though you have a constant clock signal, so as you can see over here, you have a constant clock signal over here, your triggers for your following flip-flops have an inherent delay in them. So notice how the delay increases as more flip-flops or more layers are added on. Now the sequencing of a synchronous counter is only dependent on the clock input into the flip-flop. So unlike the ripple counter, the outputs of each flip-flop do not feed into any clock inputs of other flip-flops, so it is purely dependent on the clock on your hardware system. Now an example that we're going to go through is a BCD counter, and we'll go through that shortly. Now let's look at asynchronous counters or sequences. So as you can see, a sequencer is an example of a ripple counter. It takes a clock input and sequences the outputs. The output can be up to n bits. There is no limit of how many bits you can split it off into. However, do remember that with asynchronous counters, the more flip-flops, the higher the layers that you have, the delay gets bigger and bigger. So your flip-flop on the last layer will never be in phase with the clock unless the difference is a full cycle. Now, if you look at the two tables over here, we have two examples of the truth tables of a sequencer. So a 2-bit sequencer, a 3-bit sequencer. Notice that it just sequences through a counting order, so 00, 01, 10, 11, and then returns to 00. Similarly, with a 3-bit, sequences from 000 all the way to 111, and then it resets to 000. Now let's look at an example of the 2-bit sequencer. So this is the truth table for the 2-bit sequencer. So as you can see, it goes from 00 to 01, 10, 11, and repeats that sequence. Now looking at this sequence, it's evident that we need a 2-bit counter to produce this sequence. So we need 2 flip-flops or 2 storage elements. One for the first bit, the second for the second bit. In Xilinx schematics, this would be how a 2-bit sequencer would be drawn. So as you can see, the output is inverted and then fed into the clock input of the next flip-flop. Now this can be further extended through here. So if you have a third flip-flop down at the bottom, you just need to join the inverted output of the second flip-flop into the clock input of the third. And notice how the inputs for each flip-flop is a complement of the next. So if you think about what happens in each flip-flop, it does make sense. So with flip-flop, the sequence goes from 0, 1, 0, 1, and they are just complements of the outputs. In D1, even though it's 0, 0, 1, 1, do remember that the only time your flip-flop gets edge triggered is when D0 is a 0. Because remember, at the time before D0 is 1, the input to your clock is inverted, meaning it's 0. So you have a low state, and then the next state is a high state, which means a positive edge triggered. So between the second sequence and the third sequence, you have a positive edge trigger into your second flip-flop. Again, from here, it's a more graphical visualization of what I mean when we say there are inherent delays between the signals traveling through the wires from one flip-flop to another. So notice how only the least significant bit of your sequencer is connected to the clock. There is an inherent delay between the output traveling through the wires, through the inverter, and back down into the next clock input of the flip-flop. Now, let's look at binary coded decimal counters, or BCD counters. As we said before, flip-flops hold 1 bit of information, and obviously there are 2 possible outputs in a flip-flop. It could be 0 or 1. Now, in order to convert a decimal-based system, so a radix 10 system, you will need to encode the possible outputs of 0 to 9 into binary. So from 10 possible outputs, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, in order to encode it, you need 4 bits. Now remember, hex to SSD that we did in lab 1, the inputs were from 0 to F, so 0 to 9, and then A, B, C, D, E, F. Now, for the counter to count up from 0 to 9, the truth table can be seen as below. So it's encoded into 4 bits, and at this current state, the next state should be the next number. So for example, at state 0, the next state should be 1. At state 5, the next state should be 6. And at next state 9, so 1001 is state number 9, the next state should return to 0. Now for each flip-flop, the input will be based on the current state. So as you can see, there are 4 flip-flops over here, and each one of them will have a unique Boolean expression to determine what's the next input. Do note that there are 4 flip-flops, and all 4 of them will be triggered at the same time, thus the name synchronous counters. Now, in order to complete your BCD counter, you need to derive the Boolean expression for each of the 4 flip-flops using K-maps. And do remember that in hex to SSD, we encoded from 0 to F, so 0 to 9, and then 10 to 15 is decoded as A to F. In the case of the BCD counter, we don't care about the outputs for A to F, which means outputs 10 to 15, you can use don't cares when creating your K-maps. So don't cares are X's instead of 1s or 0s, and they can be grouped together with 1s when you derive the expression. So to give you guys some guidance, in your BCD counters, the schematics should look something like this. So notice you have 4 D-type flip-flops. You have your clock input, which are all connected in parallel to the same clock source. So that's different to a ripple counter where your input is based on the previous flip-flop's output. So as you can see, the clock is connected to all 4 flip-flops and the reset's the same. Now your outputs will be Q0, Q1, Q2, Q3, so least significant bit to the most significant bit. Now you will need to obtain the Boolean expression for D0, D1, D2, and D3, and then create this combinational logic into your BCD counter. This is a blueprint of sorts of a BCD counter. The BCD counters from 0 to 9. Now, to finish off Lab 3, these are the tasks you are expected to have done by Lab 3. So, based on the 2-bit ripple counter we've shown, you should extend the 2-bit ripple counter to fit your assignment. So remember that a 2-bit ripple counter will have 4 sequences, but you have 6 digits on your MXK to display. So you need to think of a way to create a ripple counter that will account for the 6 sequences. Now you also need to extend the BCD counter to fit your assignment. Remember that one BCD counter can only count up one SSD. So let's go back to the previous page. So this say that you have this BCD counter. If you connect this BCD counter to all four of your digits, all 4 digits will show the same number at the same time, which means you'll be counting from 0000 to 1111 to 2222 and 3333 and 4444 and so forth. Now you need to find a way to link them together, say 4 instances of the BCD counter, so that you can count up in clock mode. So rather than going 0000 1111 2222 and so forth, you need to count 0000 0001 0002, and then you keep on counting until 0009, and then it ticks over at 0010. So just like how we count in our decimal system, so a base 10 system, you just need to extend the BCD counter to 4 of them and find a way to connect them together so that the next significant bit gets triggered when the previous bit resets to 0. For any further references for this lab, obviously you have your lecture videos which you should watch, as they will help you a lot with understanding a lot of the background behind the flip-flops and counters and registers, and there should also be some example videos available for going through and designing a simpler version of what is shown in today's video.